Good morning, everyone. I think we can start. I will keep a look to the waiting room, but it's 1 minute after 12, so I think we can start. And also, so welcome to this first QU-ATTO webinar, this inaugural QU-ATTO webinar. Because this is the first time that we are meeting all together, not only with the doctoral researcher, I think it would be nice to start, with a round of presentation, just introducing, name, your role in the QU-ATTO network, in order that everyone knows each other, at least for this first webinar. So I will start from myself, and then we can go by institution. Okay. So I am Giuseppe Sansone. I'm University of Freiburg, and I'm the scientific coordinator of this Marie Skłodowska-Curie network, this QU-ATTO network, and I'm really, a pleasure to see all of you here today. Let's go with the other people from Freiburg. Who wants to start? Suraj?
Hello.
Yeah.
My name is Suraj. I am a PhD student in University of Freiburg in the group of Giuseppe Sansone. Part of QU-ATTO as well.
Okay. Go pick.
Hi, my name is Kopika. I'm also working with Giuseppe Sansone at University of Freiburg. Hi, nice to meet you all.
And then at least I see Johan from Freiburg.
Hello, my name is Johan. I'm a Hiwi in the group of Giuseppe Sansone, and I'm currently working towards a master's. Hello.
Okay, thank you. Yannis, I don't know if you can talk. I see that you're running.
Hello, I'm Yannis. I'm also in the group of Giuseppe Sansone.
Mm-hmm.
And I'm also serving as a...
I think Yannis is running at Fermi, so maybe he has some problem. So let's go to Benjamin.
Hello, my name is Benjamin. I'm also working in the group of Giuseppe Sansone.
Okay, thanks. I don't see anyone else from Freiburg, so let's go to Lund.
Yeah, I can start. My name is L Huillier, and I will give the webinar in a few minutes. But I don't know. So the other people are Johan Moritzson. I don't know if he's
I think
present.
Johan should not be present. He told me that he's on, he's right now, traveling to Fermi.
Okay. And then David Busto. I'm not sure he's there. And then we have two PhD students. Victoria, I have seen her. So yes. And Tommaso, I think he's there as well. Tommaso?
Yes.
He was, yes.
Yeah, he's black, but he's there. Okay, that's it.
Okay. And also, for the doctoral researcher, we have also the pleasure that Anders is with us today.
Yeah.
Thank you, Anders. Then let's go to ICFO. I've seen Maciek before. He was briefly connected. I don't know if he's connected now. Maciek Levenstein. No. But I guess, the doctoral researcher from ICFO should be here, right?
Yeah, I'm Joseph, and I'm in Jens Bieger's group in the ATTO Second Science, and I'm the new PhD to work in quantum ATTO Second Science.
Okay. Nice to meet you. Okay, then I don't see anyone else from ICFO. Let's go to Sea Saclay. It's in Georgia.
Yeah. Hi, everyone. I'm Georgia, and I'm the PhD doctoral for under Pascal Salier group.
Okay. Thank you, George. Then we go to Madrid. Madrid.
Hello,
Yes. Yeah.
my name is Ines. I am a PhD from the group of Alicia Palacios in the UAM.
Thank you. Then amplitude I have on my list. Ah, no, sorry, Charles, you're here. Good to see you.
Hi, Giuseppe. Hello, everyone.
Yes.
So I'm from the Saclay side, and I'm an assistant professor, and I will be co-supervising Georgia, and glad to be here.
Okay, sorry, I saw you a little bit later.
That's fine.
Then let's see, I'm scrolling around, but I think the next one will be amplitude. Who is working at amplitude?
Hello, I'm Anya, and I'm working in the laboratory of Charles Fabry in collaboration with Amplitude.
Thank you, Anya. Then probably from fourth, there is no one connected because I mean they've still have to find their own PhD students.
Hello.
Arti, yes.
I'm audible. Yeah, I'm Aarti. I'm from ICFO. I'm in Matrix group.
Ah, well, perfect.
Yes.
Good to see you. Then we go to sphere photonics, and Diego, I think, is here.
Yes, my name is Diego, and I am a PhD student in sphere ultrafast photonics in collaboration with the University of Salamanca.
Hello, Diego. Then, I mean, let's go to Berlin. I'm happy to see Bernd.
Yeah, hi. I'm Bernd. I'm co-supervising our PhD student Juliana, who is here. There's also 2 more postdocs from our group who just joined the webinar, or not within the QU-ATTO project.
Mm-hmm. Hello, Bernd. And then I think we have also, I mean, someone who is not working right with experiments, right, Suman?
Oh, yes. Hi, I'm Suman, and I'm from Exponent Institute, and I'm working with Michele now.
Hello, I'm Juliana. Bernd mentioned me.
Hi. And then let's see, at least on my list, now we are at Fermi, where a lot of us are currently preparing for a beam time. So maybe Carlo wants to start.
I'm Carlo. I'm the head of the low density meta beamline, where many of you will hopefully be doing experiment in the future, and many of you are already doing that now. And I'm very pleased to meet you all.
Hi, I'm Moricto. I'm doing my PhD in the QU-ATTO network under Carlo Caligari at the LD beamline. And nice to meet you all.
I'm Oksana Plekan. Hello, everyone. I am a beamline scientist at Elettra. So hope to see you soon, guys, here.
And then I think there is also Ali, right?
Yes. Hello, everyone. I'm Ali. I'm from the group of Luca Giannussi. I'm happy to see you all in this webinar.
Hello, Ali.
Do you hear me?
Perfect. And then, I mean, at least, I mean, person that I already know, there is Hashtag from IEST. You will have a lot of opportunities to discuss with Hashtag in the upcoming weeks and months. Hello.
Oh, good afternoon, everyone. I am Astrid from IEST, and in QU-ATTO, I will be leading the photonics outreach, and we will do training already in January in Milan. Nice to see you all.
It's the first time that we see Hashtag. Hi. And then I see, is there someone, I mean, who has not introduced himself or herself? I lost a little bit track.
Giuseppe Michele is also here. Can you
Michele,
introduce him?
sure.
Oh, sorry. Okay. I'm Michele Di Fraia from CNR. And okay, I'm not directly involved in the QU-ATTO, but I'm a beamline scientist at the low density matter beamline.
Hi, Michele. Someone else? No. So then I think, I mean, I will take the word. I mean, just for general information. I mean, today we have the first webinar, and as we discussed last time, when we meet all together, the webinars will be scheduled monthly on the first day at 12. This will be the general, let's say, schedule. Of course, there can be, I mean, some variation with respect to this schedule, but we will try to keep this for the next, I mean, at least until the meeting in Trieste, and then we can rediscuss this. But today, really, I mean, it's a really, for us, a big pleasure, I mean, for me to introduce the first speaker, I mean, Professor L Huillier. And I don't think, I mean, Anne needs to such long introduction. You know Anne, I guess, very well. I mean, she's one of the founder of our research field. She received the Nobel Prize in Physics in 2023 for the discovery and the process of harmonic generation that many of us are using in our labs. And I would like also to point out, I mean, a particular aspect, I mean, of Anne's career, which is very relevant for us. Anne was really, apart from the discovery of the process of order harmonic generation, she was really the person who first started, I mean, the Marie Curie. I mean, at that time they were called Marie Curie Doctoral Network. She started the ATTO network, where I had also the opportunity to attend a few meetings, and this was really the opportunity for the first labs in Europe to group together. I mean, at a period where still there was a lot of research, preliminary research ongoing on order harmonic generation and also characterization of attosecond pulses. I don't want to take too much time, so Anne, thanks a lot for taking time in your busy schedule to deliver this first webinar, and we are looking forward to your talk.
Thank you very much. So let me try to share my screen. Do you see?
Perfect.
Yes.
Perfect.
Oh.
Thanks.
Okay. So this webinar is about fundamental concepts in high order harmonic generation. And the outline is a little bit of historical background. And this is going to be very much about the reason for the Nobel Prize in Physics 2023, what is behind this prize. And then I will talk about the single atom response, and from that, what you can deduce about the temporal and spatial properties, both of high order harmonics and attosecond pulses. And finally, I will talk about scaling laws and phase matching. So I'll follow a little bit the structure of the tutorial that I gave. But of course, with much less details. So for the mathematics, and you have to go and listen to this tutorial. So as I say, I had the pleasure to share the Nobel Prize in Physics 2023 together with Pierre Agostini and Ferenc Krauss. And you have the motivation on the slide. So I'd like to start by a little bit the background. And really this field is born from maybe broader field, which is atoms in strong laser fields. And we actually started with the invention of the laser or just afterwards. But the first theoretical prediction are already from 1931 by Maria Goeppert-Mayer. She predicted the possibility to have 2 photon excitation processes with enough light intensity. Multiphoton ionization was pioneered by Russian scientists in the 60s. Above threshold ionization was discovered by Pierre Agostini and his group in 1979. And this means that an atom can absorb more photons than what is needed for the ionization. And then multiple ionization, this was actually my thesis work in the 80s. And at this point, it became a little bit clear that it would be nice to learn more about the excitation processes by looking at light emitted from a gas of atoms exposed to a strong laser field. And this research was done at the Commissariat Énergie Atomique in Saclay, France. And we are in the end of the 80s. And let me show you pictures of both the laser that was used in this experiment and the experiment itself. It's rather old. The laser was a picosecond laser, neodymium YAG mode locked. You see the oscillator on this picture, 2 amplifiers behind. And I'm going to... And then you have the experiment. The laser is coming from the right. You have the lens here. And then we were actually looking both along the propagation axis of the laser and perpendicular to it. And just to show you how things have evolved, we were taking data by using a printer, and the pen was linked to the detector that you see here, and the paper was moving as the grating that we had in the chamber was rotating. So very, very old-fashioned. Anyway, what we observed was not fluorescence, but high order harmonics of the laser field. I see someone writing. Do you have questions already, or no? No, sorry. Okay. So so this is the one of the first spectra obtained in argon. We only observe odd harmonics, and this is because of the symmetry of the interaction. And if you plot the intensity of these harmonics as a function of order, you observe this now well-known behavior with the plateau and the cutoff. And maybe the most interesting thing was this plateau behavior, because we were really thinking in terms of perturbation theory, where you expect the polarization to be a series of powers of the electric field with the first order much larger than the third, etc. And this was not the case. This plateau behavior showed that we had non-perturbative behavior. So this is a phenomena where you need to understand the single atom response to the process described by the Schrödinger equation that you see here, but also the many atom response, the response of the whole medium, and this is described by a wave equation as you see here. And in order to have harmonic generation, you need both a strong single atom response and a certain phase matching condition, which is shown here on this cartoon, to be achieved. You need all the atoms in your medium to send waves which are in phase. And this is what is called phase matching. Progress in technology in the 90s with the invention of the chirpulse amplification, as well as a new laser material called titan sapphire and Carlin's mode locking, a new way to generate femtosecond pulses. Here you have a picture of one of the first laser using these new inventions in Europe, which was built at the LUND Laser Center. And this was really a major change in the way to study high order harmonic generation. There was really a very important transition. Here I'm showing you also all the technology. This is the instrument that we built in Saclay with my first students, Philippe Balcou, Pascal Salier, who is one of the supervisor of this quantum, one of the PI of the QU-ATTO network. And so we built this instrument containing what you have here at the top, a gas jet optics to analyze the radiation included in this chamber, as well as a photon detector, which was an electron multiplier. And what we did was we used this instrument first in Saclay using a neodymium glass laser, 1 picosecond pulse duration, so using the chirpulse amplification, but very bad repetition rate, 1 shot per minute. But then we also move this spectrometer. This was actually the beginning of European collaboration. And just to add to what Giuseppe said, actually the very first doctoral network we had on the topic, this is the time where we do not use acronyms. So it was called harmonic generation in dense laser fields. It was in the beginning of the 90s. And it was not called Marie Curie, simply doctoral network. So this was the very, very first such network. The second one was this ATTO network, which we started approximately a year 2000. So we moved this instrument around. Again, it was a European collaboration, and we moved it to Sweden and got very nice results. And this is one of the results obtained in helium, showing up to the 93rd harmonic. We actually moved it also to the United States. We moved it around looking for good lasers to work with. What about attosecond pulses? The idea came up just at the beginning of the 90s, and the idea was simply that if these harmonics are phase-locked or approximately phase-locked, then one should get a series of very short line pulses simply by interferences. So the reason for this very short light pulse, this is the case where you have not only 3 harmonics phase-locked, but 10, even shorter pulse. So the reason why we get this short pulse is first, we are at high frequency. Second, we have a broad bandwidth, which is given by all of these harmonics. Question was, are the harmonics phase-locked? And the answer to this question would be given actually with the first measurement of attosecond pulses in 2001. Progress in understanding the single atom response with a 3-step model proposed by Ken Kullander, co-worker, Paul Corkum, and also formalized by Maciek Levenstein, who is also part of this network in 1994. And this is called the strong field approximation. But I will simply describe here the very intuitive classical 3-step model. This is a cartoon illustrating this model. So what you have in brown is what is written on this equation, the atomic potential plus the light matter interaction written in the dipole approximation leading to the band of the atomic potential. So at certain times, it's possible for the electron to tunnel through this barrier. Electron is driven away, comes back, and with kinetic energy and recombine back to the ground state, leading to emission of high energy photons. And if we look at the process, what happens at each half laser period, you have different electron trajectories with electron coming back with different kinetic energies, slightly different times. So here the color shows the kinetic energy. In the time domain, you have an attosecond pulse. In the frequency domain, we have a broad band distribution, which is continuous. A little bit simplified description, because here I'm only showing what is called the short trajectory. So just to simplify, I only show this contribution, leading to a single attosecond pulse per half laser cycle. So if you have for the next half laser cycle, you have the same happening on the other side. Another attosecond pulse is emitted with the opposite sign. And if you add the two attosecond pulses, you will have a modulation of the spectrum. Modulation at frequency 2 omega, where omega is the laser frequency. And now if you repeat the process several times, then your interference spectrum will become sharper, and you recover your high order harmonic generation spectrum. So here we explain the generation of high harmonics in the time domain. And this picture here is very similar to diffraction through multiple slits. Here the slits are in the time domain, and we are looking here in the frequency domain. More progress in laser technology with going towards a really very short laser pulse, a few cycle laser pulse, and this was really pioneer in the group of Milan, called hollow fiber compression. And together with chop mirrors, this allows the possibility to get very short pulses, as well as the realization of the importance of controlling and stabilizing the carrier envelope phase, with pioneer work in particular by the group of Ursula Keller. And the carrier envelope phase is the offset between the maximum of the electric field envelope and the maximum of the oscillation of the electric field. And this led to 2001 to really a breakthrough in this field of research that motivated the Nobel Prize to Pierre Agostini and Ferencross, both the pulse measurement and the generation of isolated attosecond pulses. So Pierre Agostini, using a technique called rabbit, reconstruction of attosecond pulse, attosecond beating by interference of two photon transition, managed to show that the emission correspond to a train of a very short light pulse of duration 250 attosecond. And Ferencross isolated or managed to generate single attosecond pulses using very short light pulses to begin with, and could measure them using a streaking technique. You have one of these measurements here on this slide. The pulse duration is 250 attosecond. I'm not going to describe these techniques. I think this will be covered in future webinars. Let me just say that actually both techniques are cross-correlation techniques using the attosecond pulse and then a probe field, which is actually the fraction of the laser used to generate these pulses, and detection in using photoelectron spectroscopy of a gas. So the technique is laser-assisted photoionization. So now I'm coming to the second part of this talk. I'm going to say a little more about single atom response and what we can deduce about the temporal and spatial properties of attosecond pulses or high order harmonics. So I'm going back to the three-step model, and you can do a lot of physics by simply calculating the trajectories of the electrons as they are emitted from the by tunneling from the atomic potential. So if you have not done that already, I really encourage you to solve this very simple equation. So it's classical motion of an electron due to the Lorentz force. You should have the initial condition as indicated below, and you should calculate this trajectory that you see here. So what you have in gray is the fundamental field, and you have different electron trajectories emitted at each half laser period. So what you see is that there is a trajectory coming back with the highest slope here, which means the highest kinetic energy. This is called the cutoff trajectory. And you have trajectory which takes less time, and trajectories in red which takes longer time. These are called the short and the long trajectories. And then you should calculate the recombination time of these trajectories and calculate the corresponding velocity of the electrons, and which means the corresponding kinetic energy. And if you do that, you come with, I think, maybe the most important curve which is behind the physics of high order harmonics or attosecond pulse, which is shown here. This is the kinetic energy of the electrons as a function of return time. You see that the extent of these return times is rather small, is 0.75 times the laser period. So everything happens during a few hundred attosecond, and there is a maxima, and the maxima can be expressed as a function of the ponderomotive energy that you see here. If you don't know what it is, try to learn it. I think it's a very important concept in our field. So we find a maxima equal to 2.17 UP, and this explains the cutoff behavior of high order harmonic generation. This is the cutoff law giving the maximum photon energy equal to the ionization energy plus this 3.17 UP. You can also, and also this result also predict again the short and the long trajectories. You can also see that if you consider only the short trajectory contribution, the low energy electron will arrive earlier than the higher energy electrons, and this is almost a linear behavior, and this is what we call the atto chirp. This leads to a chirp of the attosecond emission. Is not perfect phase locking of the different harmonics. It's a certain chirp, but this return time is still included into a very short time. We are talking about maybe 100, 200 attosecond. So for the short trajectory contribution, this chirp is positive, while for the long trajectory contribution, this chirp is negative. So here I'm representing how you should think about an attosecond pulse corresponding to short trajectory contribution. It's really chirp with the red components coming first. This is a positive chirp. We can also, again, simply by looking at this curve and varying the energy, this curve is stretched towards the top. You can also deduce that the individual harmonics will also have a chirp. This is called the femtosecond chirp, and it's negative contribution. So the harmonics are always negatively chirp and the amount of this chirp depends on the energy, the photon energy. A little some word about the spatial property of the high order harmonics, which can also be deduced from this looking at this curve and looking at the how the phase of the harmonics vary with the intensity. So in space, you are interested by how the phase vary with the radial coordinate, and you can convince yourself very easily that this phase leads to a wavefront. So this is inherent to the generation of high harmonics, is divergent, as you can see here. It's always divergence and actually pretty constant as a function of the propagation direction. So if you want to now consider the wavefront of the light which is generated, you need to add the contribution from the fundamental, and this is simply equal to Q times, Q is the harmonic order times the phase of the fundamental. So this is the final phase. And so we need to add the green curve and the black curve. And depending on where you generate harmonic relative to the infrared focus, you will generate them in either a conversion beam or a divergent beam, depending on the relative strengths of these two contributions. So if you are on this side of the focus, this is obviously a divergent beam, while there is a certain plane where you generate harmonics in a flat wave front, while here you will be converging wavefront. And this means that depending on where you generate harmonics, you will have a convergent harmonic with real focus on this side, or divergent harmonic with focus, actually virtual focus before the generation median. So this is properties have been studied by many people. You have some reference here, but it's important to understand that when you plan some design and try to understand the spatial property of harmonics. Let me conclude this part by saying that there is enormous work about this idea to control the strong field physics in order to get the harmonics that you want. This can be done by adding other colors. This is an example of the spectra that you can get if you add a 2 omega field, if you add the second harmonic, and these are two different relative phase, you can either get many harmonics, including even harmonics, or you can confine the spectrum in some spectral region. You can also use the longer wavelengths in order to get very high photon energies, and this has been done by many groups. More recently, you can produce harmonics not only with linear polarization, as I've shown, but with different polarization states. And you can also produce harmonics with control orbital angular momentum. I'm showing here the group that really pioneered this work. And I think this will be part of the subject of some group of the network. Let me finish this talk by saying a few words about the second aspect of high order harmonic generation, which personally I find also very interesting. This double aspect is to me what makes the physics very, very interesting and very rich. So let me first discuss some scaling laws, and here I start by showing a propagation equation for a field E. This is a harmonic field due to polarization in the medium P. And if you look at this equation and you make a change of variable. You assume that we make a scaling with a certain parameter, which I'm calling eta square. So this is, let's assume that we make this scaling, then this term will vary as 1 over eta square. Then let's make the scaling that the radial coordinate is proportional to eta. Then this term will be again proportional to 1 over eta square. Let's assume that the density is proportional to the same factor, 1 over eta square. Then this term will be proportional to 1 over eta square. And again, we have the same factor here. So this leads to really an invariance property of this propagation equation. So now let's assume that we scale the input energy by eta square. And let's compare harmonic generation in a certain medium with a certain input energy, medium with a certain length, and atomic density, certain radius, and we get certain output energy. Now, if we simply scale up this this experiment using these scaling parameters that I showed, so we squared input energy by eta square, which means that you will get the same intensity in the nonlinear medium. We use these parameters to design the medium, and then we get an energy equal to eta square, the output energy. So I'm just simply scaling according to these scaling parameters. And if you simply look at the conversion efficiency, it will be scaling invariant. So it's more than the conversion efficiency, which is scaling invariant. It's really the equation is completely mathematically scaling invariant. And this scaling, which is very strong, explains why there are very different harmonic generation setup everywhere. You can have a very long beamline, such as the one in LUND, which I'm showing here. In such a beamline, you can generate microjoule energies. This was pioneered by the group at FORCE, as well as the group of Katsuma Midorikawa in Japan. But you can also choose to have very much more compact setups where you instead try to get high average power. A few reference here, and this is a picture of the rather compact setup used in LUND. Again, huge flexibility of the experimental condition, depending on what you would like to have, either a high energy per pulse or high average power. Phase matching. So in order to phase match harmonics, you would like the phase difference between the polarization induced in the medium and the harmonic to be equal to 0. So we want this difference in refractive indices to be equal to 0. So let's look at what is called the phase mismatch. This is this difference here. It contains 4 terms. One which is due to the neutral medium, one due to free electron, one due to focusing, and one due to the electron trajectories. So let's look at these 4 different contributions. The contribution from the neutral medium is positive. Just looking at this picture here, the refractive index in the visible is larger than 1. In the ultraviolet or extreme ultraviolet, it's less than 1. So this term is positive. Dispersion due to free electrons is negative. And usually we work with degree of ionization of typically a few %. Focusing also leads to a negative contribution. This is using Gaussian optics. This is a variation of the GUI phase. And finally, the dipole phase, the contribution from the electron trajectory in the continuum, the electron acquire phase leading to dipole phase and leading to this phase mismatch. It depends on the gradient of the intensity with respect to z. So actually, if you are close to 0, this term is negative. But you see that this term is close to 0. But you see that we have a positive term here and 2 negative contribution. If you choose the parameters of the interaction well enough, you can achieve phase matching. And very often, phase matching is discussed in terms of this contribution versus ionization versus the contribution of free electrons. It's important to mention absorption. So what does it mean that we achieve phase matching? It means that it's limited by absorption. And this is a picture showing in a very in a one-dimensional case how the harmonic intensity is varying with the length of the medium for different parameters, for different absorption lengths and coherent lengths. So you see that depending on the coherence length with respect to the absorption length, you can be on these different curves. Obviously, you don't want to be in the blue case. This is when phase matching is not really realized. You want to be in one of these curves. Maybe a realistic case is when the coherent length is equal to 4 times the absorption length. And here you see that you would like to have a length of the medium equal to 3 times the absorption length. This gives you guidance how you can choose the medium in order to optimize the processes. And these are a kind of a condition for ensuring a large harmonic yield. This was actually discussed in a very nice article by Eric Constant and co-workers. So here is a calculation of actually the conversion efficiency of the one harmonic in argon using units here which account for the geometrical scaling that I mentioned previously. So units in terms of the Rayleigh length, and here what is plotted is the pressure times the Rayleigh length. What you see is that you obtain a maximum conversion efficiency on not on a point, which would be optimal length or optimal pressure, but really on an hyperbole. And this again is another reason for the flexibility of this process. You can have different pairs of pressure and length that lead you to good phase matching as long as you are on this hyperbolic behavior. And you can even identify here different phase matching regime. One which is transient, where what is important is the degree of ionization, and this happens typically for short medium lengths, gas jet, short medium, and it's more or less independent of the pressure. But you can also have this type of behavior where the phase matching does not depend too much on the medium length, but on the other hand, depends on the pressure. So with that, I think this is what I wanted to tell you today as an introduction to the rich physics of high-order harmonic generation and attosecond pulses. So I would like to thank you very much to show here the group in LUND working on this subject with Johan Moritzson and David Busteau directly implied in this quantum ATTO network, but I think probably many people here will participate one way or another. So I would like to thank you for your attention.
Okay, thank you very much, Anne, for this beautiful presentation, for the historical background, and also for, I mean, this introduction to the process of order harmonic generation, the single atom response, and also the propagation effects. Thanks. Now it's tradition, let's say it's tradition that we are going to establish. We will have time for questions. So about 10 minutes where our doctoral researcher, but today not only the doctoral researcher can pose question to the speaker. And please use this opportunity. You can simply unmute yourself and ask with your question. Don't be shy.
Yeah.
You don't have any curiosity about order harmonic generation? Everything is crystalline clear?
Maybe I have
Please,
one
yeah.
question. Well, it's not well question. It's I have some concerns about something I have done in the past, and it mostly is related to phase matching. Okay, if we, for example, have some glass capillary in which we are generating harmonics, and we are using argon, and we are changing parameters like laser focus position or gas pressure, and by doing that, we are actually affecting phase matching conditions. And I observed different behavior when laser is focused before the center of this glass capillary or the center of the gas jet, and different behavior when the laser is focused after the center of that same jet. And the behavior is that harmonics phase match best when the laser is focused before the center of the gas jet. I observed that for different pressures, and some of our colleagues performed theoretical simulations, and they saw the similar thing. And I wanted to perform some of mine calculations where I wanted to see, okay, what exactly parameters am I changing, phase matching parameters. And I saw, okay, if I change, maybe if you have time to go on the slide when you have each of phase matching.
Yes.
Okay, thank you.
Do you see? No,
I
you
don't see
see.
anything.
No.
Not yet.
To share. I don't know which one you want to see.
The next slide, yeah, this one.
This one.
Yes, yes. Okay. Well, if I'm changing the laser focus position, okay, this first one, okay, that's obvious how it's changing, and it's similar if the laser is focused before or after the center of the gas jet. It's symmetrical. It would show symmetrical behavior. Second one, free electron dispersion. That would also, well, my point is that from everything that I'm looking at these parameters, I expect to see symmetrical behavior, but that's not what I'm seeing.
Yeah, okay. I want to give two answers to that. First, it is not going to be symmetrical because of this contribution, the dipole phase,
okay.
Which is negative on one side and positive on one side. So that's the first reason. The second reason, and it's actually above, sorry, it's coming here.
That one, yeah, I wanted to ask about that.
Yeah,
Yes.
here you really generate. I think this is the most important reason for the strong asymmetry, is that if you are on this side of the focus, you generate harmonics in a flat wavefront, and this is going to be quite different from generating harmonics in a divergent wavefront. So I see that more as an amplitude effect more than a phase effect. Amplitude effect in the sense that every point in your plane of generation will contribute the same way because the phase is the same.
Yes. Okay. Okay. Thank you so much. The 4 parameters about phase matching. Yeah, the last one was for me. Okay, this could be it. But yeah, this one.
But the one yeah, this will lead to also an asymmetric contribution.
Yes. Okay. Okay. Thank you so much.
Well, thank you. Other questions?
Yes, I have a question.
Ali, please.
Why in the 3-step model we have a plateau? In plateau, why we have the plateau and cutoff?
The plateau, I mean, it's really related to I think I have a slide. Just I like this slide. It is really related to this electronic contribution, and you can see that the probability for the electron to be ionized and come back and recombine is pretty much constant over a broad range of final energy, and this leads to this broadband plateau behavior in the spectral domain. The other way to think about it, I don't know if it helps, but if you have a short attosecond pulse emission in the time domain, you have to be broad in the spectral domain. It's just yeah, Fourier transform. But I think maybe the easiest to understand is this contribution of these different electron trajectories. The probability is very similar. So you get this plateau behavior, and the cutoff is because you have a maximum, you have a certain intensity, and you have a maximum kinetic energy than the electron can acquire, leading to this cutoff energy in the harmonic spectrum.
I didn't get it. Why the plateau is the constant energy? We have a
Because, I mean, I think because the probability to have this ionization process, tunneling, going away, coming back at different energies, these are similar.
Okay, thank you.
I have a short question, even though I'm not a student.
Hello, Maciek.
Yeah, go ahead. I'm afraid of your
so
questions.
When you talked about 4 contributions to phase matching,
yeah,
you said the dipole phase can be neglected at z equals 0, I understand, because
yeah.
in principle there are conditions in which, as far as I remember from the old days, it can be dominant actually.
Yes, you are absolutely right, and this is my answer to the first question. This term is leading to an asymmetry of phase matching and can be important, but it can be neglected if you generate at the focus of the laser. This is a simplified description and everything. And let me say one more thing. I think what is becoming more and more clear is that you cannot neglect, at least in some condition, the reshaping of the laser as it propagates through the medium. And this will also affect your HEG process, at least at high laser intensity. And in some case, I think this reshaping with the laser being defocused actually help in getting strong high order harmonics in a way which is again asymmetric. Yeah.
Yes, sure. Thank you very much, and also thank you very much for the fantastic lecture.
Thank you.
Questions? Some other question? Don't see any. Maybe Anna, I will have a question. I mean, a kind of very general one. I mean, mostly connected to the QU-ATTO network, because in the QU-ATTO network we have several projects which are focused on attosecond pulses produced by free electron laser, in particular those produced at Fermi. And I think in the last year also, let's say, thanks to the contribution of Fermi and the LCLS, it's clear that these sources, I mean, represents really something new for attosecond physics. They can generate isolated attosecond pulses, I mean, at very high photon energies. They can control independently the phase of each independent harmonic. Do you see some specific, I mean, research direction where high order harmonic generation created by tabletop sources will really not be it will not be possible for free electron laser to easily access these specific, I mean, niche or some specific field that will remain only with tabletop sources?
I see that these two sources are extremely complementary. I see many niche or many area where the free electron laser is not going to replace these tabletop sources. Fermi is a little bit in between, because you can manipulate your pulse quite a lot. But what I want to say is that maybe the most important to me, first of all, the tool that we have built, that we have developed, is not only this high harmonics and attosecond pulse. It's really the combination and the control that you have between harmonics and probe fields, infrared or visible probe field. And now we can do interferometry with this pulse, extremely precise. And I think here we are a little bit ahead of the free electron source. I don't want to say anything about Fermi again. That is a little bit special, but this and this is what, for example, enable us to measure things like density matrices. I mean, it's this very precise control that we have between this XUV radiation and other type of radiation. And let me add something here, which is a little bit provocative, but we don't care so much about the pulse duration of the attosecond pulse. What we care very much is to have a very reproducible waveforms that we can control, one relative to the other. Of course, it's nice to have short pulses, but it's really the possibility, this control that we have now in the extreme ultraviolet on these fields, on these electric fields, that before we could have with visible field, but now we have this kind of control in this extreme ultraviolet X-ray fields.
Thanks, Anne, for the answer. So, opportunity for a last question. Let me check if I see any hands. If not, Tommaso.
Yes, I have a very good question. Is it good to consider the three-step model as like a semi-classical approximation of the dependent Schrödinger equation?
I think there are better people to answer this question than me. But what I can say is that the three-step model gives a lot of physics. Maybe not the whole physics, but so much physics, yeah, to explain these processes, to use to really understand the temporal spatial properties. I think it's quite good. And now, of course, you can do better. You can use strong field approximation. You can use the result from time-dependent Schrödinger equation solution, which are better, gives, for example, absolute number of photons. So, of course, you can do better. But the three-step model really has a lot of physics. This is why it's so nice. And I would recommend, if you have not done that, solve these classical equations, because you will get an intuitive feeling about the process by yourself.
Thank you. And I think I'm remarking the importance of the three-step model. It's really the... Carlo, you have a last question? Final one?
May, you seem to have implied that the most important game both for HHG and for Fermi will be in the best phase control that we can obtain. And you have also shown that this depends on a lot of different parameters, trajectories, the shape of the wavefront, etc., etc. Do you think that there is margins for improvement, or are we pretty much at the best we can do?
I think there is a lot of margin for improvement, and this is, to be very honest with you, this is what fascinates me in this field, is that we are still working on improving HAG, although this was discovered almost 40 years ago now. But we're still working on optimizing, improving control, stretching to high photon energy or high efficiencies. And this is because we don't know everything about it. So so yes, there is, I'm convinced that you can improve. And you can improve the control that you have.
Okay, and I think probably this is the best final message. There is still a lot to do for the young researcher. I mean, entering
Yes.
the field. I mean, there is still a lot of
There
progress
is
to be done.
There is, of course, a huge area of applications to be explored, but I think we are not done with exploring the limit of these processes.
Mm-hmm.
Giuseppe, there is also a lot to do for all the researchers.
For all researchers, for all the researchers. Sorry, sure.
Yeah.
I mean, our doctoral researchers, let's say, they are now entering the field, so there is a lot of research to do. I mean, in general, let's say, for everyone. Okay, I think it's the best way to conclude. Thanks, Anne, again for taking the time for these inaugural webinars. It was really a pleasure and honor for all of us to start in this way. And for all the others, we will see each other in November, on the 6th of November, with the next webinar. Okay, thank you. Thanks,
Thank
Anne.
you.
Thanks to all of you.
Thank you,
Bye-bye.
and good luck with this network. Yeah.
Thanks.
Bye-bye.
Bye-bye.